If my screen sharing works again, hope everyone can see it. Hey, yeah, quick introduction of myself. I think Guni said already quite a bit. Yeah, I'm key account manager here in the UK for DSpace, doing that for quite a while. My main interests are more or less the right side of CVs, so yeah, virtual validation, hill testing, and so on. So I'm quite experienced in that area. So I hope I can give you an interesting presentation about virtual validation today. What are we talking about today? Quick agenda. In general, as general overview, what is SIL testing? What are the challenges? What could be the solutions for these challenges? Then a quick overview about data-driven development, which is more or less the virtual validation SIL testing area for AD and ADAS development. So it's a bit different, a bit more challenging compared to traditional SIL testing. So we'll give a quick overview about that and compare it with the classical software development process. And then, of course, because we're DSpace, a quick overview what we can offer in this area in the end. Okay, what is SIL testing? I guess, yeah, most of you will have an idea and know what it's about. So a quick overview. Yeah, most of our customers, I made the experience, switch over to agile development. So the development cycles are much quicker, yeah, much more agile, as the name says, with changing requirements. So you want to test earlier, you want to test more. And one great tool to do that is virtual testing, because you don't need to set up hardware, you don't need to get real parts. You can more or less take your software component you're just working on and run it in a virtual environment, test it against your requirements, and yeah, go back if you need to change something. So you can achieve a much higher update frequency pre-release of software, but also after your product has been released on the market. Let's talk about over-the-air updates or things like that. So yeah, virtual testing in general, software in the loop testing gives you much quicker turnaround time. Yeah, so some of the benefits I just said. One big thing is also scalability. You can run a lot more tests if you go into areas of cluster computing or cloud computing. So unlike a hardware in the loop tester where you need a big piece of hardware for each test you want to run, and you can only run it in real time, with virtual testing, you can run extremely parallelized tests, and you can also run faster in real time. So that increases, of course, also your testing speed. Yeah, what's the classic software development process? I think you all have seen the V. Let me just activate my pointer. Yeah. So yeah, left side of CV, right side of CV. Traditionally on the right side, you have the hardware in the loop testing, you have test benches, you have lab car vehicle testing or vehicle on a track testing. And yeah, more and more this area, the software in the loop testing is becoming important because yeah, all the arguments I brought before. So you test earlier, so you're moving left, shifting left on your V cycle. What can be done in different types of testing? So we call it a safety first test strategy. So certain tests can only be done in certain areas of CV. So for example, if you want to do function testing, you can't really do that in vehicles because you don't really have access to single ECU functions anymore. And if you go to the opposite end of the scale, if you want to test certain electrical tests, failure modes, and so on, you would like to do that in a vehicle because you have the real wiring harness. You can test the real startup sleep behavior and so on. And you wouldn't really like to do that in a SIL environment because you don't really have the electrical setup as the real vehicle has, and everything in between. So just I don't want to go through the whole matrix, but just to say certain types of tests are better suited for certain test requirements than others. So SIL testing doesn't mean you will get rid of hill testing and you will get rid of your prototype vehicles, but it just means you can start with certain tests earlier in the development process. Yeah, what does an ECU look like normally? If you come from an AUTOSAR background, you normally have your different software applications running on the ECUs, and you have a one-time environment, and you have your basic software, and then you have all your drivers and operating system running off the ECU. If you want to virtualize that, you need somehow to transfer this software onto a virtual, into a virtual environment. So what you can do, thanks to AutoSAR, is you can reuse your applications, you can reuse your runtime environment. Often you can also reuse the basic software. What you need to replace is, to make it available to run in a virtual environment, you need to replace it with a virtual operating system and device drivers which fitting to the environment you're running it in. Okay, this can be done then in combination with models. So you have your ECU, but of course you want to run the ECU in a certain environment. So what you would like to do maybe is having a traffic simulation, having a vehicle simulation. Could be, for example, done with DSpace ASM or any other vehicle models. Then you want to connect these systems together. So you have normally in a virtual environment some kind of simulated bus system. And of course, everything runs somehow in a virtual environment. So you need some kind of virtual operating system, for example, come on DSpace VIOS. Gives you the advantage, you can run it on any PC, you have a flexible simulation speed, so you're not bound to hard real time like in a HL system. You can parallel execute your tests. You can integrate everything into your existing tool chain. So if I see it from a DSpace perspective, you can start in a virtual environment with VIOS, use it together with the standard DSpace tools, and move over to SIL testing and use again exactly the same DSpace tools, the same DSpace automation, and so on. So everything is automatable. And of course, we're supporting all these standards like XCP, SIL API, and so on. So you can automate and calibrate your virtual ECUs like you're used to. Then, of course, there are different types of virtual ECUs depending what you want to test. So maybe you just want to test your controller models, which you call a level 0 virtual ECU. Then you want to go on application level 1. You want to also simulate your basic software. And maybe you want to add your production basic software. Then you may want to test your target binary files. And in the end, you have your real ECU. So you're getting closer and closer to the real thing. But at the same time, you're getting more complex, you need more components and so on. So there's a certain trade-off between that. During the development phase, you can use different tools to achieve these different tests. Simple is you start, let's say you're developing in Simulink, you just run your Simulink controller function you want to test directly in Simulink and you can do your first test there. Then you may want to skip into real code. You want to generate production C code for that. So you could use a production code generator, for example, DSpace Target Link or any other, and generate your optimized C code. And last but not least, you Hello, sorry, I lost my internet.
Hi, I think we're just back on. Yeah, we lost you there.
Yeah, sorry, somehow internet disconnected. Sorry for that. Yeah, I was talking about the different types of code generation for virtual ECUs. Also, you can do it from Simulink, you can do it from a code generator, you can use your production or your final ECU binary, and this gives you different ways of testing your ECUs on application level, including a simulated basic software or including the production basic software. Okay, that's more or less the basics around software and loop testing. What are the challenges? What, out of my experience in trying to sell virtual validation tools to customers, one of the biggest challenges, especially for OEMs, is where to get the virtual ECUs from. Because tier ones are quite often a bit reluctant to provide access to virtual ECUs. Yeah, first of all, because at the point in time when they should release this virtual ECUs, often they are by themselves still in an early development stage, so they don't necessarily want to give this really early development samples already to their customers. Another thing is, of course, also IP challenges, because virtual ECUs can be requiring that you need to give out open code files and so on, which could lead to IP challenges. So that seems to be one of the big stepping stones in really deploying virtual ECUs within OEMs, access to virtual ECUs from their suppliers. Potential solutions for that in the short term, I would say, is try to talk to your tier ones as early as possible, that you have a requirement for virtual ECUs, try to get it in your supplier contracts, that virtual ECUs need to be provided, and as early as possible in the development process so that everyone's prepared for it. And in the midterm, the solution will be an industry standard. At the moment, more or less earlier this year, the FMI 3.0 standard has been released, which also contains definitions for virtual ECUs. So based on that, it should be much easier to define a standardized virtual ECU format, which is not that you say, if I'm using DSpace, I have to use this format. If I'm using NI, I have to use that format. So that there will be maybe in future, next few years, a standardized virtual ECU format which can be used between tool vendors, between tier ones, between OEMs. And this, I think, will make this problem much easier and much easier to solve. On top of that, this was more or less classic software development, and there are, of course, challenges coming with developing software for autonomous vehicles, because they're coming more from the software development side of things, not so much from the systems engineering side of things. They're using different tools, so a lot more Linux usage, development of the controllers and models not necessarily done in Simulink, and more tools used like ROS or RTMaps or other tools which are more code-based than Simulink. So out of that, new standards are evolving. You have much more complex simulation scenarios because you're working with much more complex sensors, more complex simulation environments, and so on. So you need much higher degree of automation. And the biggest thing I would say is you need a lot more tests, because to test an ADAS AD system, you have to test so many different scenarios that testing this on a hill is impossible. So you need to test it virtually, and you need to test it in massive virtual tests. So it needs to be tested in the cloud. Yeah, what components do you need for an ADAS AD and also an e-mobility? Of course, you need your environment. So you need some kind of roads, you need 3D assets, and there are lots of industry standards available already for that, to be able to import road networks, to import traffic, and so on. Then, of course, you need a realistic vehicle. So you need good vehicle dynamics models, brake hydraulics, pneumatics, car, truck, and trailer, depending on what you're developing. You need powertrain models and more eDrive models to simulate your vehicle. And then the biggest thing I would say is sensor virtualization. So you need good sensor models, very accurate sensor models, which enable you to do the sensor simulation for your radar, LiDAR, camera sensors, and so on. What puts such a software in the loop or virtual simulation system for an autonomous vehicle look like? So you have, as everything is container based usually, as you run normally your simulation in a Docker container or any other container environment, and within you're running your virtual OS, and within that again you're running your virtual ECU. So in this case, you have maybe a brake ECU, an engine ECU, a steering ECU. You do some bus simulation, then you do some signal-based communication between your traffic models and your ECU. And then additionally, you may run a second Docker container, which runs your sensor simulation, radar models, camera models, LiDAR models, and then maybe a virtual machine separately, which is doing the sensor fusion and decision-making for your system. And all of that could be then again connected up via automotive Ethernet or something back to your devices under test. So it's a much more complex environment, a much more complex architecture, which needs to be modeled here. Okay, what can DSpace do in this area? We have, of course, VEOS, which is our virtual operating system, which allows you to do realistic simulation of models. So you can more or less take any FMI compatible model or any Simulink model, run it on a PC, run it in the cloud. And the good thing is if you're already using DSpace Hill and other DSpace tools, all the existing DSpace tools can be reused. So you can use your DSpace automation tool, your DSpace experiment tools, your DSpace modeling tools, everything together with VEOS. Then we are supporting, or we're trying to support all of the open standards which are out there, like SIL API, XCP, OSI, AUTOSAR, FMU, and so on. And of course, we are providing a simulation environment for each situation you may come into, for virtual ECU networks, sensor simulation, virtual vehicles, everything you can think of. We have our ASM model suite for that, which covers more or less every aspect of a vehicle. Of course, don't need to use necessarily DSpace models. We are quite open to run together with other models. Ideally, these other models support the FMI standard because then they can easily integrate it into our environment. But also, if they don't support FMI, there are ways to run them as co-simulation. And yeah, we think our VEOS system is one of the best performing simulators on the market. So from a use case scenario, you normally start with the preparation use case where you want to generate your scenarios. So we have systems where you can derive scenarios from real world scenarios, where we have recordings, sensor recordings, which you can transform into virtual scenarios, or you can just use our toolchain to build your own virtual scenarios. Then if you have these scenarios, we can parameterize them, edit them, and so on. We use our tool model desk for that. And by talking about open standards here, we're supporting ASM OpenDrive, OpenScenario, and OSI to facilitate importing world networks, scenarios, and so on. Next step is then the simulation interfacing. So as I mentioned before, we're using our ASM automotive simulation models for 3D visualization. Our older tool MotionDisk has now replaced with a new tool Aurelion, which is a sensor realistic simulation environment which generates extremely realistic environments which are needed to do, to perform sensor testing like camera testing, radar, LiDAR testing, and so on. And of course, we integrate with third-party tools like traffic flow simulations, driving simulators, OSI, FMUs, sensor integration from other suppliers, and open APIs. Then to be able to more or less do this sensor simulation, we have what we call a virtual ESI unit, which environment sensor interface unit, which allows us to feed in simulated environments from a system which runs high-power GPUs into the virtual environment to feed that information into the virtual ECU. And the equivalent for that in HAL is the environment simulation interface unit, which does the same in a hardware loop environment. Here we're supporting sensor simulation environments, of course, from DSpace themselves. We use ROS, we can use RTMaps, we can use NVIDIA, we can use any type of virtual ECU or custom code. And we support Linux and Windows environments for that. And then, of course, you want to validate everything. So our test environment is Automation Desk Connect together with Control Desk, our experiment tool, and everything can run on either in Hill environments, Galaxio, or on a various virtual environments. So all these tools are interchangeable between the two platforms. So you don't need to do any bigger changes if you want to switch from the one to the other. And if you look into cloud testing, cloud computing, web technology, you have now a tool called Simfera, which facilitates the deployment of this multi-parallel testing in the cloud. Yeah, that's more or less, again, seamless transition between offline testing and hill simulation. So yeah, all the tools can be reused for that. Yeah, that's was a quick overview of software in the loop testing. And if you have any questions, yeah, I'm here for a few more minutes. Just ask.
Great. Yeah, and thanks very much. Yeah, very interesting. It's good. Having been involved in this world many years ago, you see this evolution now and this scaling of the testing demands for automated systems. This is a new challenge for existing test engineers to grasp as well. You know, what are the big differences, big challenges that traditional test engineers will have as we move from, you know, desk-based hill testing to now cloud-based scaled up testing?
Yeah, I think the biggest thing I'm seeing is that it's a mix now of development engineers from different backgrounds. Because traditionally, we had control engineers who were quite firm working with Simulink and so on.
Yep.
But a lot of our new customers are now coming from the software development side. So they're often coming from the, mobile phone industry, computer industries, and so on. So they're used to all the traditional software development tools and the ways of doing software development. So there is quite a, I would say, gap between tool knowledge and tool usage from the traditional users and these new software developers, and getting that together and makes them work together and get a tool chain together which fulfills the requirements for both is quite a challenge. So that more or less brought in all these agile development and Git, for example, as a development environment and so on. So it's quite interesting. There's a lot of change happening in this area at the moment.
Sure. So I see a hand up. So Sonar Nandkishore. Sonar, I don't know if you had your hand up for a while. Did you have a question you'd like to pose?
Yes.
Okay, stage is yours.
I have a questions. Yeah. Yeah. So I would like to know, basically, in this virtualization, suppose if the OEM network team provides a net file, and supplier builds their software as a part of that net file based on the net file input. So based on the infrastructure availability, it may or may not be available for the vital rig or lab car, because ECU is not being yet manufactured. So where the role of virtualization comes into picture. So have you successfully gone through this kind of use case where based on net file input, you have generated some source code, and that is getting utilized, and your virtualization is successfully being able to run this use case, end-to-end use case, from net file to actual test based on that net file, where the supplier has built their software around the net file?
It has been done, but it's difficult. It depends a bit on how much input you get from the supplier. You can, of course, use your software components. You don't necessarily need to have the real vehicle networks to interconnect the software components, because in the end, in a virtual environment, it's just in the exchange of information. So if you're not really interested in the actual, let's say, FlexRay CAN Ethernet bus behavior, if you're just interested that the different software components exchange information, then within the virtual operating system, you can just define this information need to be sent from A to B, and you do that more or less without having the network files available, and you just skip the integration of the real bus networks, and then later on you can integrate that in a step when the network files become available from your vehicle team or your bus team. So it is possible, but of course it reduces the accuracy of the simulation, because you lose certain features, or I can't call those bugs or whatever, that you get network related issues in the communication between your software components or your virtual ECUs, because there would be always an optimal communication between them. But yeah, you can start testing connected virtual ECUs without having the network files available.
Yeah, I completely agree that you won't be able to achieve 100% accuracy, but at least 60 to 70% validation could be done on in a virtual world.
Yeah, so you need to see more or less what test cases you have, which are not really depending on bus influences on the tests. So certain tests can definitely be done without having the bus files.
But have you come across this kind of demand from other OEMs where they are asking for net file to software and to virtual validation?
Personally, I haven't had this requirement yet, but I'm mainly dealing with the UK, so I can't really say much about what's happening in the rest of the world. So yeah, if you're interested in that, I can. If you send me an email, I can check with my colleagues if there's anything which has been done in this area.
Thank you.
You're welcome.
Thank you. So more questions, please hands up or in the chat as well. Let me take a couple more questions. Okay, while we wait for people to think, Jan, on the question of sensors, obviously this is a massive topic now, sensors, the sensor modeling and the validation. So DSpace, are you developing in-house sensor models? Are you working with partners to develop these? What's the ecosystem that you're creating or working in?
We have our own sensor models, which is part of Aurelion now. As I mentioned, Aurelion is the successor of MotionDesk. And we had also in the past MotionDesk Sensor Sim, and this has been now moved and quite a lot improved in Aurelion. So we have now radar models, camera models, LiDAR models, and so on available in Aurelion. So we can do our own sensor simulation, but we are also working together with third parties to integrate their sensor simulation. For example, NVIDIA, we can integrate with NVIDIA sensor simulation to integrate our systems with their sensor simulation. So yeah, it's both possible.
Because I'm imagining, because what I'm saying is a trend of, there's a lot of people developing a lot of sensor models, different fidelities, different requirements, of course, and the ability to plug in sensor models into a test environment. So, let's say a particular university develops a sensor model, it's a physics-based model, and they want to now try it in a virtual environment. Do DSpace provide the ability to plug and play sensor models? Or
yeah, so you can, because our ISM models are all open models, so you can replace blocks within the models quite easily. So you could just remove the sensor simulation bit and replace it with your own models. Or if you're outside of Simulink, as long as the modeling environment you're using is FMI compatible or it generates C code, which you can just then embed on a system. Depending on how much calculation power they need, they may not run on the real-time system. They run on a PC with GPU support. But yeah, it's all possible.
Okay, very good. And the sensor models that you have, what's the process for validation? Because again, that's a very big topic. I don't know. It'd be interesting to know how DSpace tackle this. I have a sensor model, but how do I trust it?
First of all, our sensor models are normally based on public research from a lot of different universities and other public sources. So we more or less take modeling and strategies which have already been reviewed externally and try to improve them, try to integrate them into our environment and so on. So it's not something we develop from scratch and nobody's really sure if it works or not. So that's the one thing. The other thing is we are working together with customers who are more or less our development partners. So we give them access quite early to these more or less beta stages of these models. They can evaluate them against their existing models or against real world scenarios they're recording. Then we have our own test vehicles, which we can use to do sensor recordings and compare that to simulated sensor input and simulated scenarios to see how realistic we are. So it's different sources how we manage to validate them.
Very good, very interesting. Okay, any more questions? If not, then we can thank Jan for joining us this afternoon. We'll leave a 10-second gap to see if there's questions. Okay, that's great. So thanks, Jan. Thanks very much for taking time out. As always, it's very interesting to see the evolution in the industry here to support, especially the new range of technologies we're going to be dealing with around automated vehicles. And thanks to the audience as well for joining today. Our next talk will be not on the first Thursday of September because we do have our annual conference on the 1st of September. So please don't forget to register for that. Again, a plug. But it's on the 8th of September. And if there's anybody who'd like to present, we do have an open slot on the 8th. I think we've had 1 or 2 offers, but they can't do the 8th. So if you'd like to present the work of your organization, please get in touch with me or Angela, and we'll make sure that we can get a slot for you. But with that, have a really great afternoon. And Jan, thanks again. And hopefully we'll meet together soon and carry on these conversations.
Okay, thank you very much.
Thank you. Thank you to everyone. Have a great day.
You too. Bye.
Ciao, bye.
Thank you. Bye-bye.